to chat. If you're having trouble finding a teammate at this point, please reach out to me. I will be out of town tomorrow, actually this afternoon already, but so if I don't answer, no, I'm just not here. But as soon as I am, I will help you out. I won't leave you alone. But you know, use the web app, find people who are looking for teammates. If you are starting to panic that all the ideas are clean, don't worry. Come talk to me and Fateme. Tell us what you are interested in. We will find directions for you. So you know, don't feel like you are stranded in case you can't find a teammate or a project. So ideas are infinite, basically. So trust us. You will have something to work on. Okay, any questions? Okay, I failed. Any questions? Okay, then we are going to continue today where we left everything off. I'll try to be more coherent than I was at the end of the last lecture. This weight edges humbled me a little bit. So we're going to try to make sense of everything and kind of complete what we have been covering here. Just as a reminder, we talked about first replacing our transformer architecture, specifically MLP modules with a cross-layer transcoder. We pre-computed all the nonlinearities, so layer, norm, attention, and we kept them fixed in a model, which now, when we put everything together, our replacement model is basically linear. And having that model, we started to build attribution graphs, where our nodes are either input token embeddings, or feature directions, or output nodes corresponding to the logic of the next token, or those error nodes that kind of account for the difference between the CLP and the original model. And then we started to talk about what are the actual weights of the edges between two nodes, and this is where we left things off. So the plan for today is to finish our derivations of what are the weights of these edges. Then we are going to talk about a simple pruning algorithm for, okay, simple is maybe not the best word, a pruning algorithm for how to prune the nodes and edges. And that will complete basically this B part. We are going to learn how do we get pruned attribution graphs. And still with those kinds of graphs, we can have hundreds of nodes or thousands of edges. Where, remember last time when we were looking at those nice little schematics, they had maybe a handful of nodes and just a few of edges, right? It was really easy to kind of see what these schematics are representing. And if you have hundreds of nodes and thousands of edges, you don't have such a nice schematic. And what we want to get is these, what Fatima and I call vignettes, or extremely sparse feature circuits, that basically have only a handful of nodes, or maybe 20 to 60 nodes and way less edges, and you can more easily understand kind of the abstraction of what is going on within the model for a given prompt and the next token. So when we come to this point, Fatima will take over, because basically she's the one doing this work. She's an expert, she knows way more than I know. So she will cover this part and a little bit about metrics for evaluating these cross-layer transcoders that I didn't cover. Okay, is it clear what our game plan for today is? Yeah. Okay, let's get going. So the first thing we are going to talk about are those edge weights, right? Reintroduce the notation we had. So we had some source token. Sorry, excuse me, not source token, source feature. And we are interested in the effect this feature has on some higher up feature in our cross-layer transcoder. So source feature in layer LS. And we have a target feature, E, that is in a higher level in LT, where LT is larger than LS. Okay, effect of S on T as a product of how active that feature is times some virtual weight. Okay, so AS is the activation of the latent S in layer S, and this weight is the so-called virtual weight between S and D. Now, we know that our cross-layer transcoder has, for every feature, has specialized decoders for every layer that comes after that layer. So for every subsequent layer, we have a decoder matrix that stores these feature directions in the given layer and measures and we use them to kind of reconstruct every activation, every token representation that comes later on. So a natural question could be, okay, why don't we just use those in place of these virtual rates, right? Let me just remind you of that equation. So if I'm in the layer T, my reconstruction will involve all the layers up to the LT, and we will have a decoder weight between L to LT times sparse feature vector, which we are calling, I believe, Z. Z in LT plus some biases, right? So what I was raising now is, let's move everything from the HTML, which is very sensitive. So the question I'm raising is, why can't we just use these weights we have over here to say what the weight is going to be here? And yeah, two questions.
Well, I have an idea. Is it because you have a lot of noise in this?
Not really. I don't think so. Maybe there is noise, but there is something more fundamental going on here. Thank you.
For that connection between the source and the targets, this decoder one, that's only capturing the direct connection between those two, right?
Mm-hmm.
But there might also be sort of intermediate connections in between them.
Yeah.
Where there's something in between the source and the target that's still important, but
Mm-hmm.
not captured by the decoder
Yeah.
weights.
Exactly. So we have, I will call it consideration number one. One is, and I will try to visualize it. We have this feature S, and we have a feature T, right? And we have indeed this direct connection from S to T through a decoder that's specialized from going from LS to LT, right? However, this feature is going to influence every single feature in every single layer in between. So if these two are not consecutive layers, or I should say, if these two features do not live in two consecutive layers, and we have some intermediate layers, let's call this one, so just to be clear, this is layer LS, and this here is going to be a layer LT. So what if I have a layer LS plus 1 here, and I have some other feature Q? Then my feature S also impacts Q, right, through the decoder between LS and LS plus 1. And Q as well can influence T through decoder weight between LS plus 1 and LT, right? So the thing we need to consider is that, sure, S influences T, and we have the impact on the reconstruction of the token representation in layer 3T, but we also have all of these intermediate weights. And if S contributes to Q, and Q contributes to the T, what is then this accumulated contribution, right? We need to consider that. Also, in our CLTs, we are replacing only MLP layers, right? So consideration 2 is that we have MLP, and we have MLP, and so on, right? And MLP. And what we reconstruct from the first MLP, after we train the CLT, it goes in as in the input of the, the next CLT layer that replaces the next MLP module. However, in between we have those non-linearities with frozen, right? We have layer norm, and we have attention, and we have residual is linear, and so on. But we have these intermediate functions, and because we froze them, they all behave like linear maps. However, they're still changing with the influences as we come to the next MLP. The influence has changed slightly. It's scaled basically by these values over here. Okay, so now let's try to use this consideration, and our goal now is to define this value. Okay. Okay, so here we are going to use that observation. Let me write this. Okay, I'm going to write it like this. So we have AS to T is AS times virtual weight from S to T. However, we don't know what the virtual weight is, right? And we are trying to compute. Now, we are going to here use an assumption of how to calculate this. Yes, sir?
I just have a quick question about the freezing portion.
Yeah.
So, I know it makes the math more complicated, but like technically we could leave those unfrozen, right? Is it just because we're so early on in the field right now that the work just was like, well, if we freeze these, it'll make it a little easier and we can get a paper out faster, or is there some other reason?
Yeah, let me write a few equations, and then we will come maybe to the point where I will say, well, this is where we use the linearity, and then we can see whether what we think, is this a small or foundational challenge. Yeah. If I forget, remind me.
Okay.
Yeah. Okay, so we are trying to calculate this virtual weight, and here we are going to use kind of intuition about how we can go about this. And remember last time we finished off by me saying that in machine learning, very often when we want to measure importance of some input variable on some function, we are going to cast it as how sensitive the function is with respect to the input. And then we know from calculus, algebra, I don't know, analysis, wherever you learned it, that this is exactly measured by derivative of that function with respect to that input. So intuition here is we are trying to measure importance of a function of t, of some function of t, with respect to s, right? And then, again, we kind of operationalize importance through sensitivity. So we say importance is basically sensitivity of, I will now write the function as like this function of t to small changes in s. The idea being, well, if even a small change in s can cause really large changes in the function, that's an important feature, and not otherwise. And then we think, okay, what kind of tool I have in my toolbox that actually can quantify this, and you remember, oh, that's actually basically the definition of derivative. So I will say here, definition of derivative. Okay, so we are going to use that as a starting point activation of the virtual weight between S and D. So we are going to say, well, we define the weight, we are going to define it as a derivative of some function of t with respect to S. And the function we are going to use is the pre-activation of the feature t in its layer, right? So remember, we have, I'll call it here it is, right? Now I am renaming my paint. So ZLP is a ReLU, jump ReLU of encoder matrix in that layer times input to that layer, right? We call it LP. And plus biases, blah, 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 we don't care about them anymore. Okay? This value over here is the pre-activation. And this is going to give me the entire pre-activation vector, whereas I care only about the tth value in the vector, right? So I will take the tth row in the encoder weight matrix, multiply it by with this vector, input vector, and that's going to give me the value, the activation of the latent t, right? So here, let me define this function. ht is going to be the encoder row. So this is the tth row of the encoder weight matrix times xlt. Okay, so for simplicity of notation, I'm also ignoring the fact where these features occur. Just let me show you the NVIDIA one more time. Remember that okay, so here.
They added that maximize.
Oh,
function.
did you reach out to Jim?
Yeah.
That's so funny. Okay, great. Thanks, Jim. Okay, so here we have tokens, right? The fact that capital of the set containing Dallas, blah, 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 right? And every layer has decoder weight matrices, right? And we have learned certain features, but the feature set or dictionary is fixed per layer, right? And for every token, you can check whether the feature S activates or not. So if I want to be extremely precise in my notation, I wouldn't talk just about the source as these features, but rather which position, token position, I'm referring to. Because in position 1, feature S might be really active, and then for feature 5, it might be not active at all, right? So just keep that in mind, that the position is also relevant here. But now I will need to also include subscripts for position, which for obvious reasons I don't want to do. So keep that in mind as well. Okay, so I defined the pre-activation of the feature t for some token as my function with respect to which I'm calculating the sensitivity. So here I'm going to have the derivative with respect to ht, and I am going to calculate the derivative with respect to the as, and as is, remember, the activation of the S latent in its layer. So that's going to be encoder S in ls times x ls, right? And here I'm also forgot LD here. Okay? So I defined virtual weight as the derivative of the pre-activation value of feature t in its layer with respect to how active the feature S is in its layer. Okay, so now we are going to do a little bit of chain moving, right? The question now is, what is this value over here, right? So now we are going to work towards writing what that value is. Okay, so now we have DHE with respect to AS is question mark. And here we need to remember we have this situation where a lot of things are contributing to Fig. So we have, it's a slightly nuanced thing to say, so I will give you an example of very simple situations. Okay, imagine we have the token activation that is, remember last time I wrote like x base plus AS times the decoder of S with respect to LS, and okay, let me read this out. So remember that we have this notion of a residual stream, right? We have some token representation, and then we reconstruct this representation by taking the feature directions that are scaled with respect to their influence. So one way to kind of think about what the feature S is doing, it's basically contributing to a residual stream with this value over here, right? And of course, we also need to add some other vectors together to get to the actual reconstruction. So we can always break it down as, okay, some vector plus contribution of that feature direction scaled by its activation in that layer. Okay? Here, I'm just going to show you a situation where we have, we are looking into two subsequent residual streams. So I should say activations coming from, you know, two CLT layers. Yeah. Don't worry about it. Yeah. Everything is really sensitive in this corner. You touch one thing, everything falls apart. My function is really sensitive. All right, so x2, let's say, is now x1 plus AS times decoder. Okay. Okay. So let me write this. Let me explain what I wrote here. So I'm looking into how my feature in layer LS is propagating through you know, the network as it's reaching D. And I'm looking at through the lens of the residual stream, right? So I have the, you know, I'm in layer LS. The feature S is going to contribute with AS times the feature direction that is stored in LS, impacting the next CLT layer. When I come to the reconstruction that comes out of the second CLT layer, I will have this thing here, which includes this part, right? I will have how much that feature reconstructs with feature directions that are stored and specialized for going from layer LS and then 2 layers after. And I will have some more to get actual reconstruction. The point here is that I'm actually summing these impacts, right? So the impacts that I had on this layer and that layer and all the way to the layer where T lives are just adding together. And this comes nicely from having everything being linear, right? So now that everything is just being added together, we can say something about this function over here. So remember, I'm now calculating the derivative with respect to AS, and the impacts of the S coming to t are just a sum of these as times some direction, right? So now then this gives me that this equals to ls to lt minus 1 of, okay, let me write it down, then I will read it out. Okay, so basically, we have here, we have the derivative of this function here with respect to as. So I need the three-chain rule first to get what is the derivative with respect to the reconstruction. This one here times, let me just check, is this decoder or encoder? I think the decoder here. Okay, so this one. Okay. Something is suspicious here, but I can't point it out. So let's see whether I'll find a mistake. But basically, we are calculating the derivative of this function with respect to as. So we need to calculate what is the derivative with respect to the input to the MLP, and we get this through this part, through this, right? So every time I make a derivative of this part with respect to as, what I'm left with is the weight problem, right? We see that. So this is basically a derivative of as L ls times L with respect to as, right? Okay, this is good, but I don't really have this bit over here, right? This is missing. So now let's go over this a little bit. Okay, again, I'll try to kind of motivate this through an example. So I'm going to have LT is going to be L plus 1. Which means that in between layer L and LT, I have only things like layer norm and attention, which are my frozen nonlinearities. So that means that my input would look something like this. I will again read this out and explain to you. So basically, I have whatever is the output of the previous CLT reconstruction, and here I have my frozen softmax of the query transpose times key matrix, right, which I pre-computed. And if you pre-computed, then what happens with these operations is basically this. I didn't ever derive this, so you need to take this at face value. But basically, I have my frozen softmax matrix times the output matrix that, down projects the big vector, which we get from multi-headed attention into a smaller vector, the value matrix, and then times whatever is the output of the layer norm. I can say this is just a linear operator. It works like this. So if I define L to be a linear operator, that basically takes x, subtracts the mean, and divides with the frozen variance, which again is non-linear but with the computed, then all of this becomes just a linear map. And now, in some situations, not always, it depends on the positions and so on, but if I take very often, let me put it like this. If I try to calculate this derivative over here with respect to this, then what I get is A here, not the entire A, between positions I'm looking at. Again, this is a little bit confusing because I didn't drag positions with me. LP, WBT, WOT, and then encoder of T. Okay, I did skip one step, so I hope you can kind of imagine it. But we see here that the pre-activation is defined as this encoder row times the input to the MLP. Now I have defined the input like this, which means you just need to put this in the brackets and multiply it with the encoder vector, right? So that's then the pre-activation function, and when I make the derivative with respect to it, I'm going to be left with something like this. Now, I don't really care, honestly, if you don't really get how we calculated this exactly, but what I want to, and what is important for me, is that you recognize that these matrices over here, we can just think about them as one matrix, resulting matrix, and it's constant with respect to whatever is the input, because this thing is frozen, right? And it's only thing that depends on the position, and this one as well. So what you can kind of think about this is just a constant matrix, and also kind of embrace the fact that we have just multiplied everything that we collected along the way. We just, we are passing through attention. Cool, let's just multiply the frozen softmax matrix with these weight matrices. We are passing through the layer node. Don't worry, just scale it linearly by 1 over the variance and subtract the mean, right? So we're just collecting all of these things along the way and multiplying them. And this is where that idea of linearity comes, again, really handy together with here, right? It becomes really hard to then calculate everything. And this is that matrix you will see in the very long circuit tracing paper we are trying to understand. That's going to be denoted as Jacobian of, and then we'll have these positions. So I'll just write it here as L to LP. So basically, Jacobian in math has a very strong connotations, and sure we are having some derivatives here. But in the end, what we are how we are implementing this Jacobian is just by collecting all of these matrices we have along the way and multiplying them. And this is why they emphasize is in the work that this is stop Jacobian, because you're stopping where all the nonlinearities are and you're not back propagating through the nonlinear functions. So, right, let me just put everything together in the final equation, and then we will, I'll just open the paper to see that you see that the connections between equations, and then I'll make just one last walk through this. Okay, so now I have this, which I needed here, which I'm using, everything is used over here, right? And then we are going to plug it back here. So now I have just defined this Jacobian. So here, are you okay that I remove this part? It would be really bad if I started and then no. Okay, so here, I'm just expanding here. L equals Ls to Lt minus 1 times this Jacobian. And actually, to make this math work, we will need to transpose it. So trust me about encoder P transpose, Jacobian transpose times this decoder. Okay. All right, so now I have this, but this actually goes here, right? So I have AS times L. Okay. All right, this brings us to the actual end of how we calculate the weight. And now, fingers crossed, this actually looks like how they have it in the paper. Okay, it looks the same modular. I'm multiplying from the left, they are multiplying from the right. We know that this doesn't matter for matrices A, B, C, we do C, D, anyway. You know, C transpose, B transpose, things like that. So I don't think that's a relevant detail. But what we have, and I'll get to your question in a second, is we have AS, and then we have virtual weight. And this virtual weight is the sum of all of these terms over here. And now we know where these terms come from, right? They come from all of these derivations of the chain rule. So first thing we had to do was calculate we started with the, okay, we are going to define the how important one feature is to another through this intuition of using the derivatives. So this was our starting point. But to calculate this derivative, we had to use chain rule. So we broke it down into some of these terms, right? This is where we use chain rule. This addition comes from the fact that to do everything being linear, the influences of a feature just add to each other as we propagate through the layers, right? So sum comes from assuming that nonlinearities are frozen. Chain rule, then we come to this bit over here, and I didn't divide this, fully precisely. I just gave you an example of what happens when we have two subsequent CFP layers, and how with frozen nonlinearities, the impacts are changing. And the point was to say that basically what we are doing is we are just multiplying a bunch of constant matrices along the way. And we collect all of those matrices in this stock Jacobian, and when we put everything together, that brings us to this equation. Yeah?
If I look at the equation on there, it looks like the transpose is on the decoder weight matrix, not the encoder.
It's somewhere here. You just make an assumption of whether you're multiplying from the left or from the right, and then things change slightly. This is basically equivalent.
Okay.
Yeah, so I have somewhere along the way multiplied something from the right instead of left, and then everything has changed. But the logic would bring you to the same place.
Okay. Also, that summation at the top right there should be LS to L than to LT.
Yes, that's right. Thank you so much. Yeah, LS to L. Yeah, we have this. We are iterating over the layers in between. Yeah. So sorry that it isn't exactly like it's there that we are summing from the same sides, but that's just a slight detail. It's not an important one. It happens all the time. It just depends on whether you start multiplying from the left or the right from the beginning as they end. The main things you need to remember are this additive part right here, and you need to remember here that all these frozen nonlinearities along the way just multiplied by us, multiplying them over the propagation. Okay, so this has been a lot. It's really, really dense. But now you get the sense of how these edges and their weights are actually calculated. So now we are going to, let's take like a little break for this to kind of sit down for a second. And then we are going to talk about pruning. That should be fairly quick, and then Fateme, I hope you'll have enough time to jump in. But we can, you know, if you need to go over and continue on Tuesday, that's fine.
Sure.
Okay, let's take a little brief break. We get, remember here, I can choose all of the nodes, everything, and more nodes, more things I include, the busier this graph is going to look like, right? So there is a lot going on here, and sure, we get all these features, I can click on things, but it's again hard to make sense of this. Even I have way more at the disposal than I had with the full, you know, regular transformer. So we want to prune our attribution graphs, and remember this is the like a big next thing in our overall pipeline of what we are doing. So we have trained the cross-layer transcoder. It's trained. We change MLPs with the cross-layer transcoder. We freeze nonlinearities. We build the attribution graph, and now we're gonna prune it. So pruning attribution graph. And for this, we are going to need to define something called node influence, which is the impact that every single one of these nodes have on the output logic. So here, remember, I clicked on the output node Austin, which corresponds to the logic of Austin for next token prediction. Basically, it's related to the likelihood of Austin being the next token given this prompt. And we try to explain why, given this prompt, the model thinks that Austin is the highest probable option over here. So we are going to define node influence. Okay, so we are going to start with or construct unsigned adjacency metrics. And we know from, I guess, first algorithm classes that what we are storing here are basically our edges, right? So, oh, there it is. I didn't delete it. This is our, let me maybe delete a few things around it because that's our key equation. So everything we did so far led to this equation here. And now we are first going to produce the unsigned version. So just take the absolute value. And I should say from then we are going to normalize. Normalization is going to be important in the next step. I'll get to it. So, okay. So for now, we are doing this. We don't understand why, but I will mention it later. And now this is where, you know, researchers who created this work had to decide, well, how are we going to actually define the node influence, given these, you know, weights we have here and given this matrix we have defined. And basically they say, well, we are going to measure the influence through the total strength of all of the paths between two nodes. So let me write this down. defining here is first I have my normalized adjacency matrix. This kind of stores between every two nodes what is the edge weight between them, right? And what is that matrix square? For seeing that this is measuring the influence between two nodes through two-step paths, it's useful to look into something like this. So, what is a particular element NL of that matrix? Well, it is by the definition of matrix multiplication. So I'm going to write it here. So I have, right. So this is what it is, right? Sorry. I take the product of these two matrices and I take the element NL in, so row and column L. And this can be written through the sum, right? We take a nth row and we multiply it with the L column, right? Okay, but what is this? Well, that's going to be basically related to the impact that node N has on node K, and this is the impact that K has on L. So in this way, it is measuring the impact of N to L by having the intermediate node, and we are checking all of the intermediate nodes, right? Very well. So this basically means give me just direct influences, direct path from one to another. Here is, okay, measure the strength of the influence from N to L through all of the paths of a certain length, here of a path length 2, and then from path length 3, length 4, length however possible, right? I don't expect you to know this, but this is Neumann series, and it actually converges if this matrix is normalized. That's why we normalized it. So once we have normalization, this Neumann series is going to converge to identity matrix minus our adjacency matrix inverse minus identity. So, 1, 1, 1, until zeros. Okay. So now we are going to define logic influence. So for node N, logic influence in this word is defined as the IN is, I'm going to write it down. Okay, so, all right, so here we have for every possible logic among those we keep, remember this is commonly, at least in Neuropedia, such to 10. We check what is the probability of the that's assigned to the logic. Music or something like that? Other classes are more fun, it's okay. PL, probability assigned to the next token associated with that logic, right? So if I had, I don't know, I'm looking into logic that occurs in the second place of the logic vector that's associated with certain token with the vocabulary that's 1 in the vocabulary. And then I'm going to take so NL is the NL entry of the B, right? So here, this is B. so now we have a value, and our pruning algorithm then becomes pretty simple. We are just going to prune all the values. So it's going to be calculate all of the logic inputs, compute. So logic, maybe I'll just write it IN because I have the symbol. IN for every node n. Then I sort them. And I keep top k%. And k in this work is 18%, and they themselves say they chose it arbitrarily. There wasn't anything they have actually used here to decide on this parameter. Once you have, you keep 80% of those top influential nodes, you can drop all the edges that now kind of are dropped because if you have an edge between two nodes that are removed, that edge shouldn't exist anymore, right? So implicitly, you are going to drop some edges too. But you can also further remove edges. So because now these are normalized, we can also remove, at least in this paper, or keep those with edge weight, normalized edge weight, larger than 0.98, and everything else is discarded. And basically when you go to Neuropedia, and you see here, show nodes accounting for a certain number of influence, or show nodes with, feature density, that's not about edges. But if you were to create a graph yourself, remember, you can determine how many edges you are going to keep in your attribution graph. So here, node threshold is 0.7, and edge threshold is 0.9. Okay, so now we have our pruned graph, and that completes how we have produced basically panel B here. And then the issue is, as we have seen here on Neuropedia, is that many of those attribution graphs are still dense. So here some of these are bold, and this is because they connect to these nodes that are selected by a human expert into this subgraph. So once this attribution graph was created, a human expert has decided, oh, let me try to make sense of this big graph, and then they have produced this nice subgraph, which actually shows that, or suggests that the model, Gemma 2 here, is reasoning about this problem in a way you would think she should reason about it, that Dallas is in Texas, and that the capital of Texas is Austin, therefore you should say Austin, right? So when you see these bold little nice circles, that's basically what the expert had manually identified as the most related to what the model is doing here. So now, Fateme will tell us a little bit about how we can try to automatize this process. Given this dense attribution graph, which is maybe pruned already, how can we come to something that has only 20 to 60 nodes? This is an ongoing work that we are still working on and developing. But since a lot of you are interested in using some form of circuits for your projects, I think what you will end up doing is using what the best approach that Fateme has at the moment. It's not going to be perfect, but it's going to give you an opportunity to extract circuits at a larger scale than if you would try to do that manually. Are you going to use this? Oh, no, I already did it. So, yeah, here we go. Try doing it with the camera. You need a board?
nice to leave the next thing. Yeah.
Just try this thing, not because. Oh, better.
Okay. Okay, so I'm gonna talk about how we are going from panel B to panel C, so how we are going to prune the circuit that we have even further to have just a handful of nodes. So I'm gonna start with just a recap of what we're doing. So we have these replacement models. They are giving us more interpretable features. They are helping us to move away from polysymmetricity to monosymmetricity. But the issue is that they are too big. We also have automated interpretability. We have descriptions basically for each feature that we have in the circuit. And we are going to use those to help us in building that vignette at the end. And the whole goal is that we want to go from these features that we have here to mechanisms or to processes that the model follows, to go from the input tokens to this next token predictor. So yeah, we have attribution graph. It can serve as a causal explanation of model behavior, but it's too large to inspect manually. And as Anna mentioned, pruning the model to a compact subgraph or sparse feature circuit is useful. It basically shrinks the graph so much and it still keeps most of the contribution of different nodes to the output, but it still it's much larger for us for our manual inspection. So we have these vignettes, a minimal, extremely sparse subgraph that is intended to capture the circuit's core reasoning path. That's what is referred in entropic work as well. And usually experts choose around 30% of the circuit that we saw earlier to include in the vignette. This typically takes 1 to 2 hours per example. So it is really laborsome and we cannot really scale it with this limit. And typically we would have 20 to 60 nodes. And we know that some of those nodes share the same concept, so we want to group them into supernodes, and usually on average there are 7 supernodes. And this stat is coming from around less than 40 examples that we have actual manual vignettes for. So yeah, we need to scale it, and so we need to make it automated. This is familiar, so yeah, the goal is to get to this vignette. Okay, so what we first need to start with is to decide which nodes we want to keep. So as I mentioned, some of these are highlighted, meaning that we want to keep these nodes in the vignette. So what we are dealing with is we have some nodes. These nodes are going to be either the embeddings or the feature nodes. We have error nodes, and finally we have the next token predictor. Edges between them, they present influence, as we just learned. They could be positive or negative. Positive means that this node is supporting the node that it is connected to, and negative means that it's suppressing that node. And we have this final node, which is kind of like a sink, if we are thinking about this in directed acyclic graph terms. And the idea is that we want to find paths that carry the most influence from input to the sink. So similar problems like finding critical path is dealing with the same issue, that we want to simplify the graph to the most important paths. So we are dealing with the same problem here. What we are doing is that we first fix the target and sources. So we know we are going from the embeddings to the source node or the next token predicted, and we want to find score different passes that go from input to output, and at the end pick top k passes that are most important or carry the most influence. And we do that by multiplying the edge weights between the nodes that are along a path, and we also convert this to log space for stability. Once we do that, well, basically how we want to do that is we are starting in reverse topological order, meaning that we start at the top. We expand the nodes that are directly connected to this one. We score them, we keep the top k, and then we just repeat this process dynamically so that we have we can score all the passes, and then finally we keep top k. And at the end, this will give us a sequence of nodes that are in these top k passes, and also the contribution of this path. Now, one thing that could happen is that some of the nodes are shared between multiple passes, and at the end what we want to do is to keep nodes. So how we are accumulating the influence of different passes to the nodes is that we normalize the contribution of the paths so that we don't have any depth bias. So it could be the case that longer passes are more important just because they have more nodes. So we're going to normalize by the lengths of the path, and then for each node we're going to sum the influence of all passes, of all top k passes that this node belongs to. And then we are going to only keep the highly influential nodes. Okay, next is building the supernode. But before I can explain that, I need to give you a bit of background. We are borrowing an idea from data visualization. This is about skeletonization. So in this method, we are starting with a graph. We want to preserve some property of the graph, and then we want to make the graph simpler or somehow summarize the graph. So what we're doing here, we don't remove or add any nodes. We just keep the same nodes that we have, but at the end we want to group some of them so that we have a simpler graph, but we preserve some structure in it. So the first step is that we apply a topological lens to the nodes. This lens is basically how we are looking at the graph and what features we want to preserve in the graph. It could be density, centrality, symmetry, or whatever else that you might think of. For us, we want to look at the shared concepts based on the feature descriptions. So that's the thing that we want to group the nodes based on. Once we do that, we divide the nodes into subgroups. So this is called a cover. So we uniformly divide them based on the scores that they get. In this figure, it appears that the nodes on the lower layers are scored lower than the ones at the top. This is not necessarily the case with different lenses that you might choose, but just for the visualization simplicity, that's what is represented here. So we form these covers, and whatever n that we choose is basically controls for the amount of aggregation that we need. Once we have these covers, we want to group the nodes in each like blue subgroups. This again could be based on different criteria or ideas that you might have. Here we show a simple way of doing this, which is grouping the connected components into one cluster. So here you can see that this one is now one group, and this one, which is all nodes are connected, is another group. So once we form these groups, then we also need to form edges in between them. Again, we could have multiple ways of doing this. For example, we could just take the strongest edge between all the nodes in one cluster, like in this one and this one, or we could aggregate all the edges from all the nodes in this cluster to this cluster. So again, there are multiple ways for doing this, but basically these will serve as those supernodes for us. Okay, so now the topological lens that we choose for our problem is based on the feature descriptions. As I mentioned, we convert them into embeddings, and then we apply a 1D PCA on the embeddings. What this do is that basically it puts the nodes that have similar descriptions close to each other, so they will receive a similar number when we apply 1D PCA, and the nodes that have far apart descriptions, they will receive different numbers. Okay, I think because we don't have much time, I'm going too fast, but any questions?
Does the lens that you choose adjust for the weights of each feature, or does it just take into account the description?
This is just the description.
Just the description.
We could do that, or basically what the experts are doing is not exactly taking into account the influence, but the layer that the nodes are placed in the graph. That's what we are not necessarily doing here, because you could have nodes with similar functionality that are across different layers, so it would be simpler if we just group them together. Okay, so once we have the value assigned to each node, the resolution parameter that seems to be working for us is 10. This is empirical. We might find other parameters working better, but yeah, so we